All right, let's pull back the curtain on the tech you use every single day. We're going to dive into the invisible architecture, the hidden logic that makes your entire digital world tick. We're talking about data structures and algorithms.
I mean, have you ever really stopped to think about it? How does Spotify just instantly find that one song out of literally millions? Or how does an e-commerce site handle thousands of us all trying to buy something at the exact same time without just melting down? Well, I'll tell you, it's not magic, and it's definitely not just about having a fast phone. The secret is way, way cooler than that.
It really all comes down to one word: scale. Just think about the sheer numbers. When you're dealing with that much data or that many people at once, even the fastest supercomputer in the world would choke. Brute force, raw power, it just doesn't cut it. You need to be smart about it.
So let's kick things off by really digging into this massive challenge. We're talking about a level of complexity that's kind of mind-boggling. And solving it is the difference between an app that feels seamless and one that's a total nightmare to use.
So how do programmers actually do it? Well, they've got two secret weapons in their toolkit. We can think of them as the heroes of our story: the organizers, which bring order to all that digital chaos, and the recipes, which give the computer the exact instructions for what to do.
Okay, so first up, our organizer. In the programming world, this is called a data structure. And at its heart, it's just a specific way of arranging information so it's easy to work with. Think of it this way. You could have a giant, messy pile of papers on your desk, right? Total chaos. Or you could have a perfectly organized filing cabinet. One is useless, the other lets you find exactly what you need in seconds. That's a data structure.
But an organized filing cabinet is only half the battle. You also need a recipe, an algorithm. This is your game plan. It's the step-by-step guide you follow to actually use that organized data. How to find a specific file, how to add a new one, or maybe how to sort everything alphabetically.
And here's the beautiful part. When you put those two things together, you get this incredibly powerful, elegant idea that is the foundation of pretty much all software. Data structures plus algorithms equals programs. That's it. That's the whole game.
Whoa. Okay, so what are we even looking at here? This is basically a map of that programmer's toolkit. Every one of these shapes and names, stacks, queues, trees, linked lists, is a different kind of filing cabinet, a unique tool for organizing information. And just like a carpenter has to choose between a hammer and a saw, a developer picking the right data structure is one of the most important decisions they'll make.
So let's take a quick tour, shall we? We're just going to look at a couple of these tools to see how their different designs are built to solve totally different kinds of problems.
First, let's pit two of the most basic but super important structures against each other: stacks and queues. Now, they might look kind of similar, but they work on completely opposite rules, which makes them useful for very different things.
And this just lays it out perfectly. Over on the left, you've got a stack. It works on a last-in, first-out principle. The easiest way to think about it is a stack of plates. The last plate you put on top is always the first one you take off. But on the right, you've got a queue. That's first in, first out, just like a line at the grocery store. First come, first served.
And listen, this isn't just some abstract computer science thing. Think about managing a line of students waiting for help at a university finance office. A queue is the perfect and really the only fair way to handle that. It guarantees that the first person who showed up is the first person who gets helped. Simple as that.
Okay, awesome. We've got our data nice and organized. But that's only half the battle, right? It's not just about storing stuff. It's about what you can do with it. And one of the most common jobs is sorting. This is where our recipes, the algorithms, get to have their moment in the spotlight.
So I want you to imagine this. You've just been handed a list, not 5, not 50, but 5,000 student records, and your job is to sort them. The recipe you choose to do this could be the difference between it taking a split second or, long enough to go make a coffee.
All right, in this corner, we have our first contender, bubble sort. It's simple, I'll give it that. You just go through the list over and over and over, comparing 2 items at a time and swapping them if they're in the wrong order. You just keep doing that until, eventually, the biggest values kind of bubble up to the end.
But here's the problem. It is painfully slow. Why? Because it's just so inefficient. For our little list of 5,000 students, bubble sort would have to make millions upon millions of comparisons. It's a terrible, terrible choice for any list that isn't tiny. But now check this out. This is a much smarter recipe: quick sort. It uses this really clever strategy called divide and conquer. So instead of comparing every single thing one by one, it picks one item as a reference point, a pivot,
And in one go, it splits the whole list into 2 smaller piles, everything less than the pivot and everything greater. It just keeps breaking the problem down into smaller and smaller pieces until it's solved. It's brilliant.
Okay, so one feels a lot faster. But how do we actually prove that Quicksort is better? It's not enough to just time it with a stopwatch. Computer scientists needed a universal grading system, a formal report card to measure any algorithm's performance.
And that report card is called Big O notation. Now, don't let the name scare you. It's a pretty simple idea. It doesn't measure speed in seconds because that changes from computer to computer. Instead, it describes how much more work the algorithm has to do as your list gets bigger. It's a super powerful way to predict how it'll hold up under pressure. And when you put them side by side on the scoreboard, wow, it is not even a contest. Bubble sort gets a grade of O of n squared. Here, n is our 5,000 items. That means the work grows exponentially. Think 5,000 times 5,000. It's just bad. But Quicksort gets a grade of O of n log n, which is fantastic. For our list, that's the difference between the computer taking minutes to finish versus finishing in literally the blink of an eye.
So, here's the part that really matters. These concepts, they aren't just homework for programmers. Data structures and algorithms are the invisible code running your daily life. You interact with this stuff constantly, whether you realize it or not.
I mean, seriously, just think about your day. Scrolling through products on an e-commerce site, that's probably an array. Hitting undo in a text document, that's a stack in action, remembering what you did last. Your music playlist, often a linked list. And your printer queue? Yep, just like that finance office, it's a queue. They're absolutely everywhere.
So there you have it, the secret building blocks of all software. Organized data and clever recipes, turning chaos into order and making incredible things possible. So the next time your app just works perfectly, you'll know why. And the only question left is, now that you can see the pieces, what would you build?